So I go away.
So we can start the introduction, Marcus, if you want.
Okay, so it's a pleasure to have Giuseppe not here but close to Lesuche, physically closest to Lesuche of all participants probably. And he will give an introduction to neural network quantum states for many body quantum physics. So, okay, so up now for you, Giuseppe.
Yeah, thank you, Marcus, and thank you to all the organizers for inviting me and especially for putting together this great school. My contribution to the school will be about telling you something about neural network quantum states and how we use ideas taken from machine learning to study quantum problems. So today and tomorrow, I will give some introductions, some theory parts, especially, and I will use again mostly these notes that I'm going to write live with you, and then later this week there will be the tutorial by Filippo Vicentini, who is also at EPFL, who's going to tell you more about practical, if you want, implementations of what I'm going to tell you about these days, today and tomorrow. So just to give you a few useful references, so I pre-wrote this just to spare some time, but so in general, if you are interested in learning about general machine learning, so not necessarily, if you want, related to science, a great book to do that is the book by Goodfellow and others, which is called Deep Learning. And as I will tell you briefly later on, this is one of the most well-known flavors of machine learning, deep learning. And this is a very nice book with a lot of mathematics, which is not something you typically find in other books. If you want to know more about the applications or a review of the applications, we wrote a review a couple of years ago now in Reviews on Modern Physics that you can see here. For what concerns the more, if you want, applied things to variational methods, as I will tell you, there is a great book by Federico Beck and Sandro Sorella that I suggest, which is called Quantum Monte Carlo for Correlated Systems by Cambridge Press, and it contains some of the ideas, general ideas I'm going to tell you about today. There's not mention to machine learning, but I will try to cover that myself. Also for the software, there is the talk the presentation by Filippo, sorry, which is not tomorrow. I don't know why I wrote tomorrow, which is going to be later this week. And this is going to be based on essentially two software. The most important, I would say, is Netcat, which is the software you will learn to somehow use and customize to solve your own problems. And Netcat itself is based on a library which is called JAX, and Filippo will tell you a lot about this, which is the machine learning framework developed by one of the machine learning frameworks developed by Google. So this is somehow the list of useful, hopefully, references. And now let's get started. I mean, let's dive into our main goals. So let me also recap actually what the main goals of this lecture will be, just so that you know what to expect. So the first of all, I mean, we will learn how to use and know about machine learning methods in general. So, and what are the mathematical, if you want, foundations of these methods. And we will know how to apply those to quantum problems. So what are the quantum problems I will tell you about during these lectures. So these are essentially two. So ground state problems. And also dynamics. So dynamics. So let's say, so just to be concrete, so the first case would be about solving the static, if you want, the Schrödinger equation. The second one will be solving about the dynamics, so the time-dependent Schrödinger equation. And sorry, towards the end, I will also tell you something about actually learning from experiments. So this is another framework, if you want, another type of applications that I will tell you more about, which is not concerned with simulating quantum systems as this central part of the program, but is instead concerned with learning from experiments. And I will tell you what I mean with this again towards the end of my lectures. So so first of all, what is the main problem that we are going to try to address during this lecture? So the main, if you want, issue that I'm sure you've already seen discussed in many of the previous talks is related to the description of many-body quantum system, right? So what is the problem? So again, to be concrete, to be specific, as for the previous talk, I will consider during my presentations mostly discrete degrees of freedom. So for example, spins. I will not discuss directly the case of continuous degrees of freedom, like for example, electron coordinates. But the generalization of what I'm telling, what I'm discussing is relatively straightforward also to that case. So to be specific, I will focus on discrete degrees of freedom. And just to clarify the notation, for example, if you take a single, right, so a single spin 1/2, so the easiest, if you want, the quantum system you can think of, then we know that the quantum state of this guy is described completely in terms of two basis states. For example, we can fix as a basis the sigma z eigenstates, the eigenstates of sigma z. And you know that in general, again, just to clarify the notation, the quantum state of this object is described by two complex coefficients, C up and C down. So these are just the projection of the wave function onto the basis states up and down. And of course, you know that these guys are normalized. So these coefficients, C up and C down, are normalized, and they satisfy all the properties that we know from the postulates of quantum mechanics. So what is then the problem? The problem is when you have a lot of particles, when you have a lot of spins. So in this case, so if you consider the case of many spins, if you want, okay, of n spins, where n can be a large number. So in this case, you know, and again, you've seen this in the previous lectures, but it's to clarify the notations that I will be using. So in this case, you know that in general, this wave function, so this quantum state, is written as a linear combination of a lot of basis states. So for example, you have one basis state where all the spins are pointing up, associated with some coefficient, again, a complex valued coefficient. Then you have all the other coefficients. So for example, you have up, 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 then down, and this is again another of the possible basis states. Until you reach, if you want, the end, if you sort these basis states in this way, where you have all the spins down, okay? So you see that in general, I can write in a compact fashion my expansion of the wave function as a summation, as a sum over k of some coefficients, complex value coefficient ck, times some basis vectors k. Okay, so this is a compact way of writing this many-body, if you want, state. So what is this k? Because I will use it all along in the following. This k is just a collection of spin projection. Okay? So for example, so just to clarify, so I can write this as some choice of the quantum numbers sigma z on each of the spin. Okay. And, you know, in other words, this can be written also, which is equivalent again, from the postulates of quantum mechanics to the tensor product of individual spin states. Okay? So this is sigma z2 up to sigma zn. Okay? So again, you see, and this is the important point and the source of all the problems that we have in essentially many-body physics, the fact that k, so if you want the number of states that we have in this context, is exponentially large. So for the case of spins, as you've already seen in the previous lecture, this number of states k is the number of states k is 2 to the n. So we have exponentially many of these states. When n is large, this is a really large number that we can barely afford to handle. So in general, k, you can see k as an integer, if you want, that is a number that is in between 1 and 2 to the n. So just to clarify what I mean by an integer, what I'm assuming is that I can always, if you want, encode this vector of quantum numbers, again, for example, +1, -1, +1, -1, etc., up and down, if you want, in this notation, as an integer that corresponds to univocally to a given set of up and down states that I have. Okay, so you see that, for example, I guess this has been discussed before. This conversion is typically done using binary representations of your numbers. So, for example, an up is encoded as a 0, a down as a 1. So you have, for example, that each of these basis states is just an integer represented in a binary representation. But in general, you can think of this k as, again, a number that is in between 1 and 2 to the n for my spins, degrees of freedom. Okay. Now, what is then the problem? So I've hinted to the problem in the sense that we have this issue that the wave function is this exponentially large object. But in general, the problem that we have to deal with is this quantum many-body problem. And which again stems from if you want, this exponential complexity of the wave function. For example, one of the problems that we want to address a lot in physics is the problem of finding the ground state of a given Hamiltonian H. Okay, so if so H is some Hamiltonian, typically an interacting Hamiltonian of spins, of electrons, whatever your problem is. And then in this case, then you know that the main problem, one of the main problems that we would like to solve is finding the ground state, for example, of this Hamiltonian. So let's call psi 0 the ground state of this Hamiltonian, and E0 not the energy of this ground state. And in general, I mean, in the following, I will sort, if you want, my eigenenergies in a way that E0 is by definition smaller than E1, smaller than E2, smaller than the maximum number, if you want, of states that I have in my system. Okay, so you see that because the wave function is an exponentially large object, typically solving this problem exactly, so this eigenvalue problem, if you want, for this matrix for the Hamiltonian, is also exponentially complex. So just to also to connect to the previous talk, so what you do typically on a computer, if you want to solve this task, is that you define in a clever way, if you want, the matrix elements of the Hamiltonian in your computational basis. So again, in this specific case, I'm picking a computational basis that corresponds to this specific choice of quantum numbers, so just sigma z quantum numbers. You form the matrix elements, I mean, naively, of this operator, of this Hamiltonian, and this is a 2 to the n times 2 to the n matrix, okay, in general. Now, what you can do, again, naively, is that you can diagonalize it and find, if you want, all the energies and all the states of this Hamiltonian. So the cost of this operation, as you've seen in the previous lectures, can be substantially improved if you consider, I mean, with respect to this naive approach of computing all the 2 to the n matrix elements and then storing the full matrix. So you can use these Lanczos techniques, for example. But in general, I mean, the problem, for example, of finding one of these eigenstates, let's say the ground state, will be typically, so the cost of this operation, of these operations of finding one of the ground states, for example, will be still of the order 2 to the n. If, so this is an important requirement, the Hamiltonian we are dealing with is a local Hamiltonian. Okay. So I will just spend a few minutes to discuss what I mean by local Hamiltonians, because this is often a source of confusion among different communities, condenser matter, quantum information. So let me clarify what I mean by local Hamiltonian and why this family of Hamiltonians are very important, if you want, for essentially all the applications in physics. So in the following, I will be interested only in this very special family of Hamiltonians that, again, I call local Hamiltonians, borrowing a language that has been established in the quantum information, if you want, the community. And where this local has nothing to do with the locality of the interaction. So I will, for example, be interested in Coulomb-like interactions that are long range. So there's no restriction, if you want, on the range of the interaction. So by local, instead, I mean, so a very specific mathematical criterion that says that if I consider the matrix elements, for example, of my Hamiltonian in between two of the basis states, let's say K and K prime, okay? Then the number of non-zero matrix elements of this Hamiltonian, of this operator, is, so if I fix, for example, this quantum number, this bra, if you want, K, so the number of K primes such that this matrix element is non-zero is only polynomial in the number of spins. So the number of non-zero, so if you want, the number of non-zero K prime is polynomial in the number of spins. Okay? So this is what I mean by K local. Okay? So the condition, once more, is that the non-zero matrix element of the Hamiltonian are only polynomially many. So if you think about this, what this condition means, so if you think about the Hamiltonian as a matrix, really. So this means that if I fix, let's say, a row of this column, and again, the number of rows is 2 to the n, so in general, I will have 2 to the n of these rows and 2 to the n columns, of course, of this Hermitian matrix. So this condition of locality means that, for example, for a given row, K, okay, there will be only a few matrix elements that I'm writing here in blue that are non-zero. So the rest of this matrix is all zero. Okay, so this means that typically the Hamiltonians, so the matrices, if you want, that we are dealing with, have a strong sparseness. Where sparseness in this context means not that the total number of non-zero matrix elements is polynomial, because it is not, it's still exponential, but it means that if I fix a column, the number of non-zeros of these blue dots here is only polynomial in the number of spins, so it's not exponential. Okay? So this is the definition of locality I'm going to use and I'm going to work with in the following. And sorry, the most important point is that this definition is not at all restrictive for when we describe Hamiltonians that are of interest in physics, and comes from the fact that if you want many body interactions are only few body interactions. So typically there are 2 body, 3 body at most, but you don't have n body interactions. So if you have only k body interactions, then you can show that essentially the number of non-zero is a polynomial of order k, if you want, of the number of non-zero of the number of bodies. So yeah, there's a question.
Yeah, so I just wanted to understand that for any given fixed row, you're saying that there are only polynomially in many non-zero
Yes.
column entries, right?
Yes.
And there there is a fixed number of rows. So in this matrix, like if you are computing the total number of non-zero elements, that will be some n times the maximum number of the polynomial. So how does it scale exponentially? Like it is still scaling polynomial, right?
No, it doesn't, because the number of rows that you have here is 2 to the n. For each row, you have a polynomially many non-zeros. So
okay.
So the total number is 2 to the n times this polynomial.
Okay, cool. Sorry.
That's why I was saying this is not a sparse matrix in the usual sense. It's k-sparse in the sense that each row is sparse. So this is the definition. Okay? Now, so let me give you an example of why this condition is verified. For example, for some simple actually, I'm going to write this in the other page. So let me give you an example of a physical system where this condition is very well verified, okay, just to be concrete. So let me consider the simple case of a spin Hamiltonian, which is something that, again, most likely you've already seen, but a spin essentially generalized, if you want, the transverse field Ising model. So in this case, I will take some interaction matrix Jij that couples to the spin sigma z operators. Okay, so this is my classical, if you want, Ising like interaction, and then I have my quantum part with some coefficient, if you want, gamma, which is, if you want, the sum over I over all the sites. Again, this is the sum over all the sites of, for example, sigma x. So this is my transverse field in the usual jargon. Okay. Now, so can we understand? So you can immediately see here that this condition is verified of this sparseness of this k locality, because, for example, if you consider this part of the Hamiltonian, so if you want the interaction energy, the interaction part of the Hamiltonian, you see that if I fix k and I consider one of these arbitrary terms, sigma I, sigma j, you see that the only case, so this is non-zero, this object will be non-zero only if k prime, right, is equal to k, simply because sigma z by construction is diagonal in this basis representation that we picked. So you see that immediately this part of the Hamiltonian connects only to one, if you want, matrix element, which is k prime equal to k. Okay. Now, what about the off-diagonal term, which is the most interesting part, if you want, of the Hamiltonian? Well, in this case, you can also convince yourself very easily that if I fix k and I consider the matrix elements of sigma x, okay, so this will be different from zero only for one specific k prime. Again, if I fix k, there will be only one specific k prime, and specifically the k prime for which these matrix elements will be non-zero is the one where I have flipped, if you want, the spin I. So I will put a minus, if you want to say, meaning that I've flipped from, for example, from up to down or from down to up, the spin I. Okay? And then all the others are unchanged. So this is simply because if you remember the matrix form of the sigma x operator of the x Pauli matrix, 0, 1, 1, 0, if you want, this matrix, so the action of this matrix is just to flip the spin I. So if on k you have the spin is up, on the only way this object can be non-zero is if the spin in k prime is down. Okay? So you see that in total, so so for fixed k, the number of non-zero matrix elements is simply, so I have n of these terms for each of the transverse field, plus the diagonal term that again will connect only to one state. So in total, I will have n plus 1 non-zero states for this transverse field asymptotic. Okay, so you see that this is actually linear in the number of spins that you have. Okay? And you can generalize this discussion to a lot of other Hamiltonians. Essentially, all the Hamiltonians we know in a decent computational basis satisfy this very important property of locality. Now, this I mean, somehow points to the real question that we want to address during this lecture is essentially how can we go beyond, if you want, what you can do with exact diagonalization. So beyond exact diagonalization. Because, I mean, exact diagonalization is a fantastic and extremely useful technique, and you should also, and everybody should know how to work with it. However, the intrinsic problem is that typically you can find, for example, the ground state, let's say, only up to maybe 40, 45 spins. Now, I don't want to say something too far from the state of the art. So if experts in the audience can correct me, I will be happy. But let's say around 40 spins is what maybe you can do these days using large storage. And the main issue, as I guess was also said before, is that you need to store this wave function, and which again takes 2 to the n. And if you do a back of the envelope calculation, you can show that for example, to the 120. So let's say that you want to store the wave function of 120 spins. So this is equal to the number of, roughly equal to the number of atoms that you have on Earth. Okay? So this means that in principle, I mean, even if you had a very performing hard disk where you would store a bit of information using an atom, then even in this case, you will need to simulate, if you want 100 spins, to use an hard disk which is as big as planet Earth. Okay? So this is really not feasible if we want to study problems that are large, to study, for example, thermodynamical properties of quantum systems. So we have to find some alternative that somehow does not relies on storing the full wave function. And this is, if you want, the whole goal of variational methods. And I will spend a lot of time on somehow describing the philosophy of these methods and how they can be used also with machine learning. So the main idea, which again is best, I guess, explained with a picture, is that in general, we know that our states, our quantum states, we live in a huge Hilbert space. Okay, so let me denote this with some, if you want, the calligraphic H. I try to do a calligraphic H with my very bad handwriting. So we know, again, that the generic quantum state psi lives in this space, and in general, you need to specify 2 to the n coefficients for spins in this vector space for spins to somehow have access to exactly to all the properties. However, and this is a very important observation that several people have done, typically we are not interested in describing the most general, if you want, wave function, right? So we are not really interested in a random state in this Hilbert space whose coefficients are random. We don't care about those because they don't have any, if you want, interesting or not too interesting physical properties. What we are really interested in is targeting physical states. So typically, these are a much smaller subset, I would say an exponentially smaller subset of the all possible states that you can write and you can think of in this large Hilbert space. And for example, I mean, these are, again, solutions of the ground state problem for some local Hamiltonian. So again, this is not the most general matrix 2 to the n you can write. It's a very specific local Hamiltonian. So again, there's a lot of constraints in the structure of the coefficients of the wave function. Or there can be other things. So for example, the dynamics of a quantum system as a quantum system as induced by a local Hamiltonian, again, is not a random state, it's a very structured state that we have. So the main goal of variational method is to try to address, if you want, this corner, so this smaller region of my Hilbert or vector space in a way that is still feasible using, if you want, reasonable computational resources. Okay. So so how do we do that? So this is the goal of accessing, if you want, corners of this larger space. So the way that we do it with the variational method is very simple, I mean, at least conceptually. So we write some state, and we have this state depend on a large set of parameters, W. I'm calling them W for reasons that will be clear in the following, but these are, if you want, just parameters. Okay? You can think of this as a collection of many, possibly millions of, if you want, of parameters. These are just, again, variational parameters. Okay. So, and to be really utterly specific, so this means that what I'm doing is that I'm picking my coefficients in the expansion that I wrote before to be dependent on these weights. Okay? So if I write a generic expansion of my many-body wave function with this, if you want, a 2 to the n, right, coefficients, I'm taking this coefficient, ck, a generic coefficient, to depend on a subset, I mean, on some parameters. And the key assumption, of course, is that I want this number of parameters to be only polynomial in the number of spins or particles that I have in my problems. Okay, so I'm parameterizing the coefficient of my wave function, and I mean, one typical way of finding these parameters is through the variational principle. So the main idea in general of this variational method is that we can find optimal weights or optimal parameters by optimization. Okay. So what do I mean? I mean, I'm pretty sure that all of you are familiar with the standard, with the variational principle in quantum mechanics. So let's say that I want to find an approximation of the ground state of a given Hamiltonian taking this specific form. So what I do is that I form the expectation value of the Hamiltonian, if you want, on this family of states that depends on this parameter W. So I just write it in general for some unnormalized state like this. So just the expectation value of the Hamiltonian divided by the norm of the wave function. Again, I'm not necessarily assuming that my wave function is normalized, so I have to take into account this. And you know, by virtue of the variational principle, that this object is equal or is larger or equal than the exact ground state energy. Okay, so this is very easy to show actually. So I will just give you a small hint on how to do that. But in general, you can write your psi W as a linear combination of the exact eigenstates of the Hamiltonian. And if you do that, you will end up to writing your expectation value of the energy as a convex combination of the exact energies Ek with some positive coefficients. So, and again, you have a normalization here. Okay, which by definition, so again, since I'm sorting, if you want, my energies in a way that E0 is the lowest energy. So by definition, then this object, since it's a convex combination of positive coefficients, will be by definition larger than E0. Okay, where I've defined Bk to be just the overlap, if you want, between my kth eigenvector, the exact so this is the exact eigenvector of my of my Hamiltonian and my variational state psi w. Okay. So this is a one-line proof that you can do easily by yourself. But in general, the main principle that then the principles that we will use are based on the fact that we can rephrase most quantum mechanical problems, for example, the ground state problems, as an optimization problem. So for the ground state, it's clear what the optimization problem is, and this one is very easy to write down. For other problems, such as the dynamics, I will tell you about other variational principles that we use, but all of these are based on the idea of optimizing, so minimizing some cost function, the energy in this case, and finding the optimal parameters W that correspond to the ground state. Okay? Okay, now, there are then mainly two, if you want, two main classes of variational states, two main classes of variational states. So this is again to try to connect also with the notations and maybe the things that you already heard before, because it's important, I think, to have a unified vision of these variational methods. But in general, so you can think that there are, again, two classes. So a first one, class number one, if you want, which is a class of variational states, psi w, as I'm writing them here, such that I can compute this energy function, or functional, it's a function actually, EW exactly. I mean, I'm putting exactly in quotation marks because by exactly I mean apart from if you want rounding errors on a machine, right? So it's but what I mean is that there is an efficient, if you want, algorithm to compute the expectation value of the Hamiltonian in essentially an exact way, apart from rounding errors. Okay. Then there is a second family of variational states that is that is more general actually than the first family, in which you can compute this expectation value of the energy of the Hamiltonian approximately. Okay. By approximately, I mean not in a completely chaotic way, but I mean in an approximate but controlled way. Okay. So this means that I have, if you want, some parameter, and I will tell you what this parameter is, that I can tune in order to have really essentially as accurate as I want approximation to my ground state energy. But these two differ from somehow conceptually from the way the answers are constructed and the way also the physical properties of the are computed on these variational states. So just to give you an example of states that belong to the first category, so example of the first kind, okay? One very easy, I would say, conceptually easy state, variational state, maybe the first variational state you've heard about, I mean, during your lectures, are mean field states. Okay. So what is a mean field state? Well, it's very variational state. It's very easy. So the idea is that you have your psi w, again, your variational wave function, and you write it. This is the essence, if you want, of the mean field approximation, as a tensor product of some individual, if you want, single spin or single particle wave functions. Okay. Phi 1, phi 2, up to phi n if I have n spins. So this is the essence of the mean field approximation, because by definition now, all the properties of this many body state are actually independent. So they depend only on the single particle, single spin wave function. So for example, I can pick this phi I and phi j to be orthonormal without loss of generality. And I can also pick, and these are my variational parameters, if you want, in this terminology. So essentially, the variational parameters will be the projection of this individual spin state onto the computational basis. So again, sigma iz can be either up or down. So in general, so this will be my, if you want, weight wi, my variational parameter, and for each spin, so for each site, I will have two possibilities. So one parameter that describes if you want, the amplitude of having that spin up, and one other parameter which is the amplitude of having that spin down. Okay? And then, of course, by virtue of normalization, I have also a constraint on the if you want, on the sum of the squares of these variational parameters. But you see that in general, this variational state depends on, you see, you have essentially roughly 2n variational parameters. So this is one very simple variational state. And again, this belongs to the first class because you can compute expectation values exactly. So for example, let's take our favorite spin Hamiltonian, the transverse field Ising model. So let's say that you want to compute the expectation value, for example, of the transverse field part. So again, the expectation value of sigma ix. Okay. Now I'm not writing the normalization because this state is automatically normalized by construction. But you see immediately that since I've picked a tensor product structure for my state, then the only non-trivial part that I have to consider is the action of this sigma ix operator onto the phi I, if you want, state. So this means that the expectation value of this is equal to simply sigma, to phi I. So my single particle, my single spin wave function of sigma ix. Okay. And since phi I is a wave function which is described only by two parameters, I can compute this expectation value essentially with two operations. I'm not writing the details of how you do that because it's really a trivial consequence of what I wrote here. So you see that computing sigma x can be done in order two operations. Computing expectation value of sigma z can also be done in order n operations. I'm not writing that explicitly. But in general, you can convince yourself that computing the expectation value of a many-body Hamiltonian onto a mean field state can be done very efficiently. So there's a question by Lorenzo. Okay.
Just a point I missed, but so phi is always the same single particle state on all sides?
Not necessarily. So that's why I put an index I here. So you can typically have these amplitudes depend also on the site. So this is the more general mean field you can do. Yes. So for example, if you don't have translational invariance, it makes sense to have these parameters depend on the site. Yeah.
Okay, thank you.
Okay, so this is the mean field state, but what can we do beyond the mean field? So this is again just to connect to what you've seen before. But another thing that you can do in the many body case, where now I'm really taking the most general wave function ckw with some basis vectors k. One alternative to the mean field state, which is much more powerful, the mean field is, for example, matrix product states. So again, you've seen this during these lectures, but it's to connect to this, if you want, language that I'm using. So in this language, then the coefficients that you have when you parameterize your wave function with a matrix product state, so with a tensor network in one dimension, as you've seen, can be written as the product of n matrices. So M1 that will depend only on sigma 1z, M2 that will depend on sigma 2z, and so on and so forth until you reach the end of this chain, if you want. Okay, and you've seen from the previous lectures that these matrices, apart from the borders, I'm not considering the boundary effects, if you want, but in the bulk of this representation, so these matrices have chi-square entries, where chi, as you've seen in the other lectures, is known as the bond dimension of the MPS. Okay. So, and again, I'm writing all of this because I also wanted to tell you that the number now of variational parameters that you have in this very specific representation, which is much more powerful than mean field because you can describe essentially all the ground states of one-dimensional Hamiltonians, is of the order, if you want, of chi-square, so this bond dimension square, times the number of sides. And again, a polynomial in the number of sides if chi is a finite number. And also this belongs to the first family of variational states because if you write, for example, the expectation value again of a sigma x operator on this family of variational states, as you've seen during the previous lecture. So for example, if you use the Penrose notation to write a matrix for the states, so here I'm considering a matrix for the states of 3 sides, okay? So these are my tensors. So this is my tensor M2, if you want, with 3 legs, so 3 indices. These are my border tensors M1 and M3 in this case. They have only 2 legs, okay? And this is my bra, if you want, my psi W. And then you've seen that if you want to compute sigma x, let's say the expectation value of some operator, let's say sigma ix, as in the previous example. So this will be, again, a matrix with 2 legs. And you have to attach these legs only to the index that correspond to the physical, if you want, site on which this operator acts on. So this is all the principle of tensor contractions that I guess you've seen in the previous lectures. And then when the beautiful part of MPS is that you have, you can write this expectation value essentially as a contraction of these tensors, as a multiplication of these high-dimensional objects that have at most 3 legs. And at the end of what you've seen, essentially computing the expectation value of the energy. So for example, computing the expectation value of the energy in the case of the transfer field Ising model will be something that has a cost of in 1 dimension, which is proportional to typically to chi cube. Okay, so again, you can compute exactly, apart from rounding off errors, the expectation value of arbitrary operators. Now, so this is the family of states that belong to this first class of variational states for which you can compute exactly expectation values. So typically, so the fact that you can compute expectation values exactly comes with some limitations. So there are some beautiful parts of the story that, again, the fact that you can write most of these expectations in terms of very efficient operations. But typically, I mean, roughly speaking, there are some limitations that coming from, if you want, the strong locality of these variational states. So again, what you've seen, but this is just a motivation to see why we want to do other kind of wave function. Essentially, if you have this, for example, these variational states based on tensors, then, for example, matrix product states, tensor networks, then you can represent typically efficiently states that have area law. Okay, so again, I'm picking my large states, large Hilbert space of all the possible states. Now I'm interested in the physical part of my states. Okay. And a subset of these physical states are those that have area law. So there are some of those that are not physical, some that are physical, but in general, so I will have a subset of area law states. So these are states for which the entanglement entropy scales only like the area, the surface of the systems, not like the volume of the system. However, there is a lot of other, if you want, interesting quantum states that instead have a volume law. So volume law states are those, again, for which the entanglement scales typically like the volume of the system, and there are those for which typically you cannot exploit efficiently these local tensor networks representations. So we would like to find some representations that are more general, if you want. And example of volume laws we are interested in are especially those that are related to the dynamics. So for example, long-term dynamics of physical systems have volume law. Typically high temperature states or some excited states typically have a volume law. Open quantum systems are mostly characterized by volume law states. So there's all sort of very interesting physics that happens with volume law states, and we would like to have a way also to characterize those volume law states. Okay, so if we want to do that, it's essentially a theorem. You have to go beyond this class 1, if you want, of quantum states that allow you to compute expectation values exactly. So then we enter the realm of this second class, if you want, so second type of variational states in my own classification. So this is not very standard, but relatively standard, for which, again, we cannot compute EW exactly, but we can have some essentially arbitrary accurate approximations of EW. So to give you some reference, so this notion has been formalized mathematically in a very nice paper in the quantum information community by Van den Nest. So the paper is on the archive. It's archive 09 11 16 24 from 2009. So this is the basis of the formalized aspects that I will tell you a little bit about in the following. But in practice, this family of variational states has been used, if you want, without this nice formalization since the beginning of computational physics, essentially. But it's been used since, the first application done by Macmillan, who's a pioneer in this field of variational Monte Carlo. This is how these families typically are, this family of techniques are called, from the 1960s. Okay, so essentially this is a very well-known family of variational states that again typically goes under the name of variational Monte Carlo. I will tell you why this is called like that. But by the definition, so let's try to be a bit formal here. So the definition that I will use in the following is that of so-called computationally efficient, or actually tractable quantum states. Okay, so all the states I will deal with in the following, all the variational states are what is defined to be in this paper computationally tractable. So for a state to be computationally tractable, it has to satisfy two properties. So the first property is that you can compute, if you want, the amplitude of this state on a given basis vector k efficiently. Okay, so I give you again one string or one integer, if you want, in between 0 and 2 to the n minus 1, or 1 and 2 to the n, and I want you to be able to compute this the amplitude efficiently, okay, for a given variational state. So this is the requirement A. And then the requirement B, which is extremely important, is that you are able to sample also efficiently, and let's say more or less efficiently, and I will tell you what I mean by this, from a probability distribution P of k, which is defined to be just the square of k psi square. And if your wave function is not normalized, you want to normalize it to psi. Okay. Again, I will discuss in detail why we need these two requirements, but for the moment, all the variational states I will be interested in the following satisfy essentially these two requirements. So you can compute these coefficients efficiently, and you can sample. So you can sample from this probability distribution efficiently or almost efficiently. So then this is if you want, the theorem that has been shown, which is non-trivial. I mean, even for the more expert in the audience, which has been proven by Van den Nest. The theorem tells you that if you have an expectation value, okay, of some local operator, or again, local in the sense of k-local, like in quantum information, like the Hamiltonians we were discussing at the beginning. So this object can be computed essentially in polynomial time with fixed accuracy. So this is an informal statement of the theorem, but the main point is that even though we don't know how to compute expectation values of Hamiltonians or other operators exactly as for tensor networks, say, or mean field states, there is a specific strategy that I'm going to discuss in a second that allows us to compute essentially with arbitrary accuracy, more or less, the expectation value of arbitrary local operators. So how does this work, and why do we need these two requirements that have been somehow formalized in this paper? Well, the idea, so if you want to estimate some properties, so again, I want to estimate the expectation value of the Hamiltonian, the energy. I want to estimate the expectation value of my spin operator. So those are all properties, are those operators that I want to estimate. So in general, I want to estimate, let's say, the expectation value of some operator, which by definition is the expectation value of this operator over psi. Okay. Then the idea is that you rewrite this inserting two completeness. So you insert the completeness here and the completeness here as the sum over k and a sum over k prime of psi, and I put here my first completeness, k, okay? Then I have my operator O, and I have my second completeness, k prime, and then I have my state psi. This is just the numerator. And then at the denominator, you can do the same thing, just with just one completeness that will give you essentially psi k modulus square. So here I'm assuming that psi is complex in general. So the idea then, I mean, which is again a beautiful observation, I think first done by Macmillan, is that you can rewrite this as the expectation value over k of a positive object, psi k square. So essentially now what I'm doing is that I'm multiplying and dividing by psi of k. So I multiply this, I multiply this object by psi of k, and I divide by psi of k. Okay, so when I multiply here, I get the square of psi of k square. And then I have the sum over k prime of this matrix element of my favorite operator. And then I have psi over k prime divided by what I multiplied there. Okay. And then at the denominator, I have the same thing. I mean, I have the same probability, if you want, distribution, psi k square. So the important point to observe here is that I've rewritten my quantum expectation value of the operator O as a statistical expectation value over a probability distribution given by psi k square. So this is, if you want, exactly this probability distribution I was telling you about here. So this Born, if you want, the distribution. This is a Born distribution because whenever you measure, I mean, experimentally, your quantum system in your computational basis, for example, you measure sigma z, you do a projective measurement for a quantum system, then you know that the measurements will be distributed according to psi square. So exactly this distribution. Okay? And indeed, it's not a coincidence that also the expectation value can be written as essentially expectation value over this Born distribution P of k, that again you can immediately see here. Right? So this is now my P of k, the normalized version of P of k, okay? Of an estimator, which is the quantity in red brackets, that for unfortunate reasons in the community is called the local estimator of the operator O. Okay? So by definition, I'm just rewriting things, but you can read them from what I already wrote. So pk is again psi k squared divided by the normalizations of psi, so the normalized, if you want, probability density, and OLOC, so this estimator, if you want, of this operator, is given by the sum over k prime of these matrix elements okay. Now you see immediately that if I can, if I satisfy the two requirements given by Van den Ness, so that I can sample from psi k, so I can generate some, if you want, integers k that are distributing according to this probability distribution, and I can compute psi of k for an arbitrary k in essentially polynomial time, then you see immediately that I can compute this local estimator also in polynomial time. And the ingredient that, if you've been listening to the first things I was saying, is also necessary, is that the operator O has to be local, because you want this summation has to run over a number of elements which is not too large, so it has to be only polynomial. So, but you see that if the operator O is local, k-local, then the summation is not on all the 2 to the n states, but only on the matrix elements for which this O is non-zero, which are again only n, order n. And then computing this ratio of wave functions is done efficiently because we satisfy condition A. Okay? So if I satisfy these two conditions, so sampling from P and sampling and computing this psi k also efficiently, then I can compute the local energy, the local estimator of my operator in polynomial time, and I can also estimate this with sampling using a very simple strategy now of this stochastic estimate of properties. So what do I do is very easy. So the first step is that I generate a lot of quantum numbers, if you want, of basis states in my representation. So let's call them K1, K2, okay, Km. So these are, again, you can think that each K is an integer, a binary number, if you want, in between 0 and 2 to the n minus 1, if you prefer. Or you can think of K as a vector of plus or minus 1. Those are all identical representations. But again, the requirement is that you sample these objects from P of K. So, and this is the first thing. So you generate M of these samples. Okay? Then in the second step, you estimate the expectation value of the quantum operator as a statistical expectation value, because you can write now that O, so the expectation value of my quantum operator, is essentially by the law of large numbers, approximate by 1 over m, so the simple mean of this local estimator. Sorry. Okay, so you see, it's very easy. I generate m samples. For each of these samples, K1, K2, Km, I compute the local energy, and I can do that efficiently by construction. And then the expectation value is just approximated by the mean of this local energy. So in this sense, the local energy plays the role of some effective classical, if you want, estimator of an arbitrary quantum operator. And now, what is the accuracy that you get? as all, if you want, stochastic estimates that work with estimating means with samples, then you know that the error that you do in approximating the average of the operator O using essentially m samples goes like the square root of the variance, if you want, of this estimator, divided by the number of samples m. Okay. Again, the tricky part for those of you who are interested in these aspects is to show that this variance is finite. Okay. So this is non-trivial to show, actually, and this is a bit of the tricky part in the demonstration of Van der Nest, because you see that here the denominator I have a psi of k, so this in principle can diverge and give rise to infinite variance, actually. But there are ways to ensure that, and also do actually better estimator than this one, that guarantee that the variance is finite. So if you guarantee that the variance is finite, then you automatically have an algorithm that always converges with polynomial accuracy. So essentially, you increase the number of samples and you reduce the error as much as you want on these quantities. Okay. And again, I mean, this is just another way of rephrasing it. But again, the error on the estimate of your operator, for example, on the energy, will go to zero essentially when the number of samples goes to infinity. Okay, so so maybe I will do now a 5 minutes break so that we can all brief. So I will start at 12:12. Okay. Yeah, so if you have questions, maybe I can answer them now or maybe later. Thank you.
Oh, thanks, Giuseppe. Are there questions? For me, it was very clear.
Okay, great. So this is then a good point to stop, and then I will yeah, we'll come back in 5 minutes. See you.
Okay.
Marcus.
Yes.
So maybe I just say that because there was a discussion on the Slack, so about the videos that are not on YouTube, Katarina, Adam Naum, and Anusha. So I'm preparing the Google Drive with these videos that will be accessible only for the students of the school. And today I think they will be available, okay? And so we solved the problem, and now I will, after Giuseppe, I will erase the video from the Zoom, and so there will be space, okay?
Okay, so the other announcement is just to remind that we'll have an additional poster session tomorrow afternoon at 1:30.
Valentin is a question.
Yes, but in fact, it's more for Giuseppe. I don't know if he's still here or not, but so I can. It's not about the organization.
Yeah, I'm here. Yeah, go ahead.
Oh, okay. So if I may, it's just like how to know if we have a quantum state that we can computationally track. Like if I have an Hamiltonian, how do I know that? Okay, well, I can computationally track the quantum state that I'm interested in.
Yeah, so the question is actually not about the Hamiltonian. It's about the family of variational states you are working with.
Yes.
So there are some families of variational states that are computationally tractable. So if you satisfy these two properties that I wrote before, okay. So let me try to share again, actually. Are you seeing my screen? Oh, yes, no, yes. Okay. So if you satisfy these two properties here, so if you're for quantum state, you can compute actually unnormalized amplitude on an arbitrary state k, basis state k, and if you can sample from this probability distribution, then you are computationally tractable. So these are the two conditions. But again, this is not directly related to the Hamiltonian. This is really a property of the wave function, if you want. I don't know if this is clear.
Yes, okay. This part is totally clear, but then maybe it will be the next part, like if this kind of computationally trackable state quantum state may solve the problem that I want, like how to know if the area that I can search with these variational states can.
Sure. Yes, so this is essentially, I would say, an open question in quantum information, which is very hard to answer to. So for a given Hamiltonian, it's hard to say. For an arbitrary Hamiltonian, it's essentially impossible to say if some state is the. I mean, if you can write a computationally tractable state that corresponds, for example, to the ground state of the Hamiltonian. Yeah. Unfortunately, there is no general tool to do that. Yeah.
And I don't know, some tools like if there is some property, then we can know that there are some trackable states. I don't know if there is some symmetries that can make. If we add some information to this arbitrary Hamiltonian, can we
yes,
are we able to do something?
Right. So okay, let me be maybe more specific. But okay, so of course, so if you know that your Hamiltonian is a single particle Hamiltonian, then you know that the mean field state is exact, right? So if you put constraints on your Hamiltonians, yes, in that case, you can find. So these typically are called parent Hamiltonians in the sense that you can find. Sons and daughters of these Hamiltonians that are exact ground states or eigenstates of this Hamiltonian. So again, if you take Hamiltonian, which is the sum of single particle contributions, then you know that this family of mean field states is exact. There are other Hamiltonians that contain two-body interactions, for which we know also that there are Laughlin, Jastrow states, other things that are known to be exact. The question is, if you give me a general Hamiltonian I know nothing about, then in that case, nobody can tell you anything.
Okay, thank you. And just maybe a quick one. And are we able to say that if we're gonna make a mistake or not, or it's totally impossible to know if how?
Yes. So I will. I will come back to this point. Yeah. So essentially, the idea is that you can, when you minimize the energy, you can also try to quantify how far or how close you are from the ground state, the exact ground state.
Okay, thank you.
Okay. So maybe it's a good time to start again. Sorry for the short break, but that's what we have. Now, coming back to my definition of computationally tractable state. So you've seen that there are two main ingredients. So the first one is computing these efficiently, and again, this will depend on the family of states. We'll see in the following some interesting family of states for which this can be done. But I want to discuss first the requirement B. So what does it mean that I have to sample, right, from this probability distribution? How can I do it? For example, if I satisfy only condition A, right? So this brings me to this notion of of Markov chain Monte Carlo. I think there's somebody who was not muted. I don't know. Okay, great. No. I don't know, Marcus, if you can. Okay, great. Okay, so So this is the idea of Markov chain Monte Carlo. Which is a much broader family of methods to sample from given probability distributions. So I'm sure that you've already seen it. But the idea of this family of approaches is that you generate a chain, right, of states. So this k, for example, these integers k that go in between 0 and 2 to the n minus 1, using a probabilistic process. Okay, so we will have, if you want, a strategy to generate a sequence of m states that in which, if you want, each of these states depends only on the previous one directly. So that's why this is called the Markov chain. And which are characterized by the following properties. So essentially, you can define a transition probability T of going from the state I to the state k I plus 1. Okay, so this Markov chain Monte Carlo is a family of probabilistic, if you want, tools that, given the current state of the chain, which is again an integer k, ki, essentially proposes a new state k of I plus 1 with a certain set of rules that are specified by the specific process that we are taking. So in practice, you can show that you can sample from your target distribution. So let's say that my target distribution now is P of k, as I wrote before, if you satisfy the so-called detailed balance condition. In other words, if this transition probability satisfies this property, so that the pk times the transition from tk to tk prime is equal to p of k prime times this transition probability from going to k prime to k. So this is a very famous condition that I'm sure everybody of you has seen before, but it's called the detailed balance. Okay. So physically speaking, this means that the probability of being in a certain configuration k times the probability of leaving this configuration to go to another state is equal to the probability of being in that other state times the probability of leaving that other state, right? So there's a sort of equilibrium that is reached when you satisfy this condition. And then if you satisfy this condition, all the points that you generate with this transition probability, so this T is what we can call a global transition kernel. Then you can show that asymptotically the point, essentially all this k that you generate with this global transition kernel are distributed according to P of k, your target distribution, which is what we want, right? I mean, specifically one of the most famous realization of this detailed balance condition, but not the only one, is the Metropolis Hastings algorithm. So you can show that if you take this global transition kernel T, again, from going to K to K prime, as the product of what is called a local transition kernel T, from going to K prime, times an acceptance probability. So you decompose this transition into two steps. Okay, so a first step in which you propose a local modification to your K. So that's why we can call this a local transition kernel, as opposed to the global transition kernel that I have here. Okay. So for example, you can think that I have my spins, I pick one at random and I flip it, as you do it in the classical leasing model. So this is the same. So my local transition is really this thing that I pick one spin and I flip it. Okay. And then I have another important element in this Metropolis algorithm, which is the acceptance probability. So I propose to flip a spin, let's say with this local transition kernel, And then I will say that the next step is equal to this K prime with some fixed probability, which is this acceptance probability. This is the most important, or if you want, revolutionary aspect of this Metropolis-Hastings approach. And you can show that the detailed balance is verified if you use as an acceptance probability the minimum. So this is the famous formula between 1 and the ratio of P of K prime. So the probability, the configuration, the state that you are proposing over P of K times this local transition kernels from going from K prime to K divided by from K to K prime. Some of you might have seen the version of this algorithm where these two factors are not here. So that's the standard Metropolis algorithm. But if you take a transition, local transition probability, which is not symmetric when you exchange K and K prime, then you have to take into account also this factor in the acceptance probability. This is just a note for those of you for all of you who have already seen the Metropolis algorithm. And the most important point now is that if we go back to the problem of sampling from my P of K, my square of the wave function, you see that estimating this ratio, so P of K prime over P of K, okay, this is equivalent to computing the ratio of two wave function amplitudes squared. Okay? So you see that it is efficient to estimate this acceptance probability, if you want. So all the process that I'm describing, all this Metropolis algorithm approach is efficiently realized because the condition A allows me to compute, if you want, this psi k for an arbitrary k or k prime in polynomial time. So I can compute this ratio also efficiently. And again, because psi of k is efficiently computed. And notice that here I don't really need the normalization of the wave function, which is also nice, because the normalization cancels, right? So when you have psi divided by the same, but with k, so you immediately see that you don't need really the exact normalization. So even if your amplitudes are unnormalized, this is not a problem because you can still use this Metropolis approach. Okay, so this gives you then a very conceptually easy approach to obtain estimates for an arbitrary variational state that satisfies these two conditions. So that's essentially one condition, which is computing the amplitude of the unnormalized wave function. And then the resulting algorithm is again very, very easy. So first of all, you so let's say at order 0, you generate a random, if you want, state k0. Okay, so a random integer, if you want, in between.
Yes. Just to interrupt shortly, there's a short question. Why is it enough to get the absolute value instead of the complex ratio of amplitudes?
Okay. So the reason is that, as you can see, so as we wrote before from this in this problem, we need to sample from psi squared, right, to generate so the condition that I wrote here is that we are able to sample from psi squared, okay, and the psi square really counts when we multiply and divide here from psi. So in other words, you need to sample from psi square because that's the only thing we need when we estimate the properties. However, the complex part of the wave function is needed when you need to compute the local estimator OLOC. So in that case, you see that OLOC depends clearly also on the phase of the wave function. Okay. Is that clear?
Okay, should be. Yes.
Okay. So then the resulting algorithm, if you want to do all of this, is that at first you generate some random, if you want, uniformly distributed if you don't know better, integer in between, if you want 0 and 2 to the n minus 1, okay? Then what you do is that you propose with your local transition, right? You propose a new state, let's say k prime. Okay, so for example, you pick a random site, you flip it, and this is your k prime now. So you generate k prime. Then the second step is that you compute this ratio. So this p of k prime over p of k, and possibly if your transition probability is not symmetric, you have to compute also this ratio. Okay. Then you draw a random number, xi, which is in between 0 and 1, uniformly distributed. And then the fourth and the final step, if you want, of one, so this is just one, if you want, step in this Markov chain, then you have to repeat this m times, okay? But the fourth and final step is if essentially this xi, so this random number, is larger than the ratio that again you can compute efficiently, then you say that the next element in my sequence, so k of I plus 1 is equal to k prime. So you accept this state. Otherwise, if xi is smaller than r, then the next element in my Markov chain will be equal to the current one. So I'm not modifying my state. Okay? So this is what you do to sample from psi square. And then again, the sequence of state that I will generate with this approach, k1, ki plus 1, etc., up to some large number m. These are all distributed according to p of k. Okay. I'm somehow skipping some important parts that somehow related to the convergence of this approach to the exact probability distribution. But these are the same conditions that you have in all metropolis approaches. Typically, you need this T to be ergodic, so you have to span over the possible configurations. And also, you also need essentially, which is the hard thing to, yeah, so essentially ergodicity is the hard thing to demonstrate, and also the correlation time. So essentially how long it will take to your Markov chain to converge. Okay. So Marcus, how much time do I still have?
I guess a quarter of an hour because.
Okay, great.
Roughly.
Okay, so this is then the first requirements. So the requirements that we have identified that are crucial is essentially being able to sample from the wave function and be able to compute these amplitudes for arbitrary k. Now, the important requirement that we haven't addressed yet, which somehow is what you are all expecting, is how do we parameterize this wave function, right? So how do we find a general parameterization of this wave function that would allow us, for example, to target volume states or other fields? Okay? So this is the main question, if you want, that we want to address now. So how can we parameterize general quantum states? Okay. And this is where, I mean, machine learning enters the game. So this is where I will tell you why we use machine learning. So just to give you a first idea of why we do that, but essentially machine learning to a large extent can be thought of as a very powerful set of, if you never heard about what machine learning is, one of the main applications or one of the most powerful realizations of machine learning concern functional approximations. So machine learning are a set of computational techniques to, in most cases, to perform functional approximations. So these are functional approximations algorithms. So let's say that your goal is to try to represent some general function f that can depend, for example, on the number of inputs, x1 up to xn, which it can be large as you want. Okay. So just to give you some specific example, one typical task which people to which people have applied machine learning is image classification. So what is the problem of image classification? So in this case, for example, I give you a sequence of images, okay? Typically for historical reasons of cats and dogs. I don't know why, but so I have, let's say, M images. And what you can think is that I have a digital version of this image, for example, like taken by a digital camera or in a JPEG format, whatever. And then each of these corresponds to some high-dimensional vector xi. Okay. And I have M of these high-dimensional vectors. So in practice, what are these high-dimensional vectors? So again, if I have, for example, a black and white picture, then these vectors, so let's say the first component, so this will be itself a vector with n components, where n is the number of pixels now that I have in my image, and each of these objects, each of these components of this vector can be either 0 or 1, okay, which correspond to having a pixel on or off in this image. If I have a black and white image, with colors is a bit more complicated, but let's focus on black and white. So then I have this sequence of axes, if you want, a lot of these axes, a lot of these images. And then my task, if you want, is to find some function, f again of x, okay, that returns some y, or if you want xi, returns some y. That classifies these images. So, for example, I can imagine that I have a sequence of handwritten images. So, so you can think that my image contains the handwritten, like I'm writing it now, number 3, and I want this function to take this sequence of pixels, just 0 and 1s, and tell me, oh, listen, this is a 3, number 3. Okay, so this is the goal, for example, of an OCR, right, software. Those when you scan a piece of paper and then you want this software to tell you what you've written in that piece of paper. This is exactly this kind of the function that we want to understand and we want to approximate here. Okay, so this is a high-dimensional function that, again, if you have another number written like this, you can have a lot, thousands of pixels that are just 0 and 1s, but the function should return just 2 as an output. Okay. So you see that here I'm after finding a representation of this function that for an arbitrary, if you want, input image, will return some classification of this image to be a 3, a 2, a 1, or a cat, or a dog, or Marcus, Giuseppe. If you are on Facebook, that's exactly what happens with image classification. So this is the high-dimensional function that we want to approximate in this simple problem. There are more complex problems where also we are after approximating high-dimensional functions. So one of these is game playing, not only because it's fun, but it's also a very hard problem in artificial intelligence. So, for example, if your game is the game of Go or chess, so there are 2 opponents, and each of them has, I don't know, their pieces on some squares. If you're playing chess, for example, right? And so essentially, you can think that the state of the game is very well quantified by, again, an n by n matrix of entries. So this is, again, your vector x, like an image. Okay? And like an image, this vector x1 up to xn, you can always find an encoding in which this can be described by a binary essentially variable. So for example, you can think that 0 means that these pixels, or if you want, this part of the board is empty, so there's no piece on this. And 1, it means that is occupied. Okay? So this is just one possible convention. And then what you really want is to find a function, again, a very high dimensional, very complicated function, that given one of these configurations of pieces will return you a yi. So again, x now are the positions of the pieces, and y can be, for example, where should I put my pieces in order to win the game. Okay, so this can be thought as the new positions, for example, for my pieces. And again, you can think in this case that y is also either an integer or just a binary number. It doesn't really matter. But you see that also in this case, what you are really after is approximating a very high dimensional function. And again, this is one of the tasks for which machine learning is really excellent. So as an example, in 2016, DeepMind, which is one of the most advanced companies working on machine learning, essentially for the first time managed to beat the world champion of Go using a machine learning technique based again on ideas on how to approximate this function with high dimensional representations. Okay. And again, state-of-the-art applications of machine learning are found in image classification. So that's why when you tag a person on an image, Facebook immediately recognizes who that person is, because all of these are based on these functional approximation techniques. Okay, so what are then these functions that we can use to approximate these high-dimensional unknown objects, unknown f? Well, typically, and this is what we will be interested also in the following. So what high-dimensional functions? The kind of high-dimensional functions that we will consider are what are known as artificial neural networks. Okay? So you can think that an artificial neural network is nothing but a high-dimensional parameterized function. So just to give you a specific example of typical network that is used in deep learning. These are what people call feed-forward neural networks. So I have again an f of x that I want to parameterize, and I parameterize this as the composition of linear and nonlinear transformations. So let me just write the form, and then I will explain you what it means. So this G is my nonlinearity, then I have my linear transformation W, then I have another maybe nonlinearity, then I have a linear transformation W, and again a nonlinearity, okay, and then I have W1, and then I have my X. Okay, so let me clarify what this symbols means and what this is. So again, this is a feed-forward, so-called feed-forward deep network. And you typically read this object from the right to the left, okay? So again, this is a function of input x. So my input x is here on the right. X again is a vector of, again, a vector of n components in general, okay? So we start layer by layer, as it's called. So the first layer is the input. So layers, so these are my layers. And if you want the layer number 0, or the first layer, is my vector, my input vector, which is again a vector that generally belongs to Rn. Okay, it has a dimensionality of n. Then what you do in the first layer, which is here written by this W matrix, is that you multiply this vector with a matrix W. So what you do is that you multiply with some W1 matrix ij your input vector xj. Okay, I'm just doing matrix vector multiplication, and out of this I get another vector h1 of I, which belongs now to R of some dimensionality, which is the dimensionality of the, if you want, inner index, the inner index I of this matrix, which is an arbitrary, if you want, the dimensionality that you have to fix at the beginning, that I'm calling here L1. Okay, so I have a matrix that has a dimensionality which is L1 times n. So this is my matrix, my linear transformation W. And then if you want, at the second step, what you do is that you apply a non-linearity to this vector. So what you do is that you apply this g function, which is a nonlinear function, component-wise. So this notation gh applied on a vector, component I, means that I'm applying a nonlinear function to all the components of this vector. So it means that the output of this nonlinear transformation is itself another vector. So I take a vector, and as an output, I also have another vector that I can call h prime, if you want, one of I, okay? Which by definition is equal to g applied on the ith component of my vector. And the output, again, the size of this vector h prime is the same as before. So it's L1. I'm not changing the dimensionality. I'm just applying to all the components a nonlinear transformation G. So just to conclude on this special form, if you want, which is known as the feed-forward network, I will give you a graphical representation, which is known and very used a lot in this context of these networks. So that when you see this written, you know what we are talking about. So essentially, the typical graphical representations of these neural networks are done like this. So you have your input vector on the left. So this is to confuse you now, because typically you put, so the input is here on the right if you write like this, but if you do a graphical representation, the input is on the left. So just be careful when you look at this. So I have my variables that I can just write as dots. Why not? They can be 0, 1, or whatever other number you have. Then I have, so this is my 0th layer. Okay, so this is layer 0. Then in the first layer, I have some of these other variables that I called h prime in my notation here. Okay, so sorry, h in my notation. So this, for example, would be h1. This would be h2 and h3. And then, I mean, typically, we also already assume that these are the result of the nonlinearity. So that's when what you write, it can be slightly confusing at first, but h prime is really meant, so these nodes here are really meant to be the result of the application of the nonlinearity to this vector. Okay? So these are really what I'm plotting here in this first layer as really are already the result of the nonlinearity. Okay? And then, I mean, again, you can combine this transformation because you can apply again a nonlinear, a linear and then a nonlinear transformation, and you have, I don't know, h prime 1, h prime, so this would be h prime 1, okay, with this other index here, okay. This is a 2. So you see the idea. I don't want to complicate too much the notation, but you see more or less how this works. Until you reach the final output, and the final output will be, I don't know, 1 or more numbers that correspond to to the output of your function. So, and again, just to be to clarify the notation, the widths of the network are nothing but this L, so the sides of these matrices. So L1 would be the width of the first layer, and until you reach the last layer that I call D in my notation. Okay. So if you want the number of variables if you want the sides of these vectors, intermediate vectors, is the width of the network. It makes sense because the more, if you want, variables you take, so the larger is the first index of these matrices. If you want, you can represent this as having more neurons in the middle. Okay? So these are the widths of the network. And then, of course, the depth. So this is the width. And then the depth is just how many layers you have. So how many, if you want, linear layers, because I told you that there is this ambiguity where linear and nonlinear are associated to the same layer. But typically, so again, the depth of the network will be just D, so how many transformations you are doing, okay? So this is clear and intuitive. And typically, these are called deep networks because you take a lot of these transformations in a cascade. The activation functions, so what are called activation functions in jargon, are nothing but these nonlinear transformations, so these nonlinear functions G. Okay. So GI of X, if you want, is one-dimensional function. So these are the so-called activation functions. So typical examples are, I don't know, the tanh, or I mean, for some reason I'll tell you in the next time, log cosh, and others. So these are typically inspired by the physiology of the brain or other physical considerations. And the idea is that when some signal arrives on this neuron, so you can think of this as an idealization of the brain, then the output of this neuron will be non-zero depending on this nonlinear function. So typically, if you take, for example, this nonlinear function to be a step function, you can think of this as a neuron that starts spiking, so starts activating itself only if the incoming signal is larger than a certain threshold. Okay, so that's why it's important to have a nonlinearity, because you can also represent high-dimensional functions. Okay, so I think that I should really finish now. Sorry for the delay, yeah, I'm available for more questions if you have.
Thank you very much. So you should not feel sorry. I should feel very sorry because I was just mixing up the schedule. So are there questions? I see one question by Anton.
Thank you for the lecture. And I'd like to ask several questions regarding this step of sampling the states with from the Born distribution.
Yes.
My question is as follows. How do you actually ensure convergence of a particular state to your distribution? Because from what we know, it typically rests on the, let's say, eigenvalues of the corresponding transition matrix and the gap between them. So, but in practice, you are not to calculate all of those. It's kind of impractical. So you somehow introduce empirical tests on conversion so that you've made enough steps to ensure that K is actually belongs to your desired distribution. So I'd like to know how this is practically done in these types of approaches to estimate the expectation value.
Yeah, so precisely, you clarified all the issues that are more general related to Monte Carlo methods, if you want. I mean, what you can do, I mean, again, there is no exact answer to your question. There are just things that people do and that empirically tend to work. But to estimate the convergence, one of the things you can do is that you plot, if you want, your observable, some observable you want to estimate. And you will see that at the beginning, there will be a thermalization phase in which the mean, if you want, where essentially the value of your observable local estimator will be far from the asymptotic mean. So you will clearly see that you have to discard some small, typically hopefully large or large, depending on the application, number of samples. So somehow by eye, you can look at this convergence of the observables and see that you have to discard, I don't know, the first 1,000 samples and then keep only the others. This can be quantified more precisely, typically using more Markov chains. So this is one possibility. So if the means of these Markov chains are too far apart from each other, independent Markov chains, typically this is an indication of lack of ergodicity.
To this, I must ask whether it is fine to study the convergence purely by examining the observable, because as far as I know, it is typically a standard situation that all sorts of local observables thermalize much faster than the actual distribution. I mean that even before you reach the true limiting distribution of K that you aim for, all sorts of local observables, such as the estimator O-loc itself, right? They will thermalize, but this doesn't mean that it actually thermalizes to a proper value. So
sure.
At this point, I know that this is a kind of a general problem. There is no like legit answer to it. So I was just wondering what is actually done in practice. So
what is done in practice is what I just described to you. So you take a few observables, not only one. Mm-hmm. Again, notice that yes, so you can take other observables, even non-local correlation functions, if this is your worry. Mm-hmm. So you can take, for example, non-local in space now correlation functions. So these, as you mentioned, tend to converge slower. So this will give you an upper bound, or will give you an estimate of the convergence time. I'm not claiming that this is an exact solution to the problem. The exact solution to the problem is to remove the Monte Carlo sampling. So this is what we do with other families of states. But I'm not going to tell you about this. I'm just maybe flashing you the idea. So if you want to remove that and make sure that you are converging, you have to use what we call autoregressive quantum states.
I'm just writing this down. And what about various ways of exact sampling, such as, let's say, I've heard something like backpropagation Monte Carlo.
Sorry, what?
I've heard some things like backpropagation Monte Carlo. Is this some sort of it or something different?
I'm not sure what backpropagation Monte Carlo is.
Okay. Just that, okay.
Maybe Hamiltonian Monte Carlo. I don't know. But okay. So just to give you, so these allow you to do exact sampling.
Mm-hmm.
So the idea, very briefly, is that you write your variational amplitudes as a product of some, let's call them psi I, that depend only on psi. Sorry. Okay, yes, so let's do this for spin, otherwise it's a bit annoying. So let's do it that has sigma 1, sigma n, okay. Then, so the idea is that you write it with a parameterization that is a sort of conditional, like a conditional probability. So you know that if you have a probability, you can always write it as a product of conditionals. So we have generalized this to the case where you write a wave function as a product of conditionals, so to speak, wave functions, where these psi I are themselves parameterized by a neural network, for example. I mean, maybe I'm going too far for today, but if you do this, then you can show that you can do exact sampling using, this is a conditional structure of the wave function. Again, if you are
Okay,
interested, I can tell you more details later, but this is the idea.
Yeah, probably we can get back to that later. Yeah, thanks.
No, but this is an excellent point. This is why that's the reason why also we develop these techniques, because we don't want to rely on Markov chain Monte Carlo, which is known to have some issues in convergence, but we really want to be exact in the sum.
Okay, so maybe there's no more question. It's a good point to stop for lunch and meet later at 4 o'clock or on Casa, if you like. Giuseppe, can you put your notes on the Slack? Possible
Yes.
at some point?
Yeah. I was planning to put them online at some point. Yes.
Okay.
I will send them to you. I mean, whatever works for you.
Okay. So thanks again.
Thank you.
Thank you very much. So I'll see you tomorrow.